diagram. In that we have 3 points, that is phases. In that we have total 7 phases. First is alpha ferrite, second delta ferrite, austenite, cementite, liquid iron, lead and perlite. Okay, then we have 3 reactions. In that first eutectic reaction, second perieutectic reaction, and third eutectoid reaction. Okay, then at the end we are going to cover the point, that is critical temperatures are A0, A1, A2, A3 and ACM. So these are the 3 basic points or the sub points we are going to cover. Those are the 7 phases, 3 reactions and 5 critical temperatures. Okay, so next, this is the actual iron carbide equilibrium diagram looks like. Okay, in this is a graphical representation of what we can see. On the y-axis there is a temperatures and x-axis we have the carbon percentages. Okay, so see, this is a equilibrium diagram or phase diagram where we can see the various phases in it, like this is alpha ferrite phase, this is delta ferrite phase, this is austenite phase, here we have liquid iron phase, here we have cementite phase, that is Fe3C, this is lead and here we have the perlite. Okay, so these are these 7 phases which are present in iron carbon equilibrium diagram. It is the effect of the temperature on y-axis and the carbon composition on the x-axis. So this whole is a graphical representation of effect of temperature and effect of composition on the various phases present in steel and cast iron. Okay, then see, on y-axis we have temperature. It is start with the 0, then we have second temperature A0, that is 210 degrees Celsius, A1 727 degrees Celsius, A2 768 degrees Celsius, then 910 degrees Celsius, 1147 degrees Celsius, 1400 degrees Celsius, 1492 degrees Celsius and 1539 degree Celsius. Okay, so these are the some temperatures we have taken for our diagram. Then on the x-axis we have some carbon composition, or you can see here we have written that is percentage of carbon by weight. Okay, so see here we have first, that is 0% carbon, then here we have 0.008% carbon, then 0.025% carbon, 0.8% carbon, 2% carbon, 4.3% carbon and 6.61% carbon. So on y-axis we have temperatures, on x-axis we have carbon percentage. Okay, so in this, see, at the bottom we have steel and cast iron. So this is steel. As I said earlier, steel and cast iron both are the ferrous materials, okay, which contain iron as a base metal. So steel and cast iron both are the alloys of what? Iron and carbon. Okay, so here see here, steel is something, it is alloy which contain carbon below 2%. Okay, from 0.008% to 2% carbon, it is a steel, and the cast iron which contain carbon from 2 to 6.67%. Okay, then here we are going to study in this whole diagram that we have total 7 phases. In that first, this is alpha ferrite, second delta ferrite, third austenite, fourth here we have cementite, fifth liquid iron, fifth lead and seventh that is perlite. Okay, so these are the 7 phases we are going to study. Then we have 3 reactions, that is first eutectic reaction, here we have the eutectoid reaction and here we have the peridictic reaction. Okay, then we have the 5 critical temperatures, that is A0 210 degrees Celsius, A1 727 degrees Celsius, A2 768 degrees Celsius, then we have A3, that is a range from 910 to 727, and last we have ACM, that is again also a range from 727 to 1147 degrees Celsius. So this is what about the iron carbide equilibrium diagram. Okay, so we will go to the next. So see, we start with the starting brief. Okay, so this is iron carbide equilibrium diagram. So what they written, it is a graphical representation of the effect of temperature and composition on the phases present in a alloy. Okay, on y-axis we have temperature, on x-axis we have the carbon composition. So the whole is nothing but the effect of temperature and composition on a steel and cast iron alloys phases. If we cannot increase the temperature, if we cannot increase the composition of carbon, we doesn't get any phase. As we are increasing the temperature, same way we are increasing the carbon percentage, we are getting the different phases. Okay, so when you heat some material, which by increasing its carbon percentage, we are getting the different types of phases. Okay, so this is a graphical representation of the effect of temperature and composition. Okay, so next, an equilibrium diagram or the phase diagram is constructed by plotting temperature on y-axis. As you know, on y-axis we have temperatures, and percentage of composition, that is carbon percentage, on x-axis from 0 to 6.67%. Okay, then it also shows the range of temperatures and composition within which various phases are stable. Just like in steel we have different phases, like alpha ferrite is in steel, austenite is in steel, delta ferrite is in steel, then cementite, this is Fe3C, will be in cast iron. Okay, so the composition and temperature will show the different types of phases. Okay, next, iron is an allotropic or polymorphism material. As we have studied in the first lecture of this chapter, that is what is by allotropy or polymorphism. This is something which is the material which have same composition but different crystal structure. So see here what they are given: from 0 degrees Celsius to 910 degrees Celsius, means from 0 to this much, up to this, whatever the phase below 910 will show the BCC structure, that is body centered cubic structure. Okay, and from 910 to 1400 degrees Celsius, from this to 1400 degrees Celsius up to this much. Okay, this will show the FCC structure, that is face centered cubic structure. And from 1400 to 1539 degrees Celsius, means from this 1400 degrees Celsius to this 1539 degrees Celsius up to this, it can show the again BCC structure, that is body centered cubic structure. Means from 0 to 910 it show the, means up to this whole structure will be in BCC structure. Okay, above this will be in a face centered cubic structure, and above again 1400 you will see everything in a BCC structure. Okay, so this is nothing but a allotropic nature of a iron. Okay, so we will move next. So see, Curie point of iron is at 768 degrees Celsius. What is my Curie point? Curie point is nothing but the point where the magnetic property of material changes. Okay, see, when we heat any material which has some magnetic property, as we are going to heat the material for higher temperatures, it will lose its magnetic property. Same way here, when we start to heat any iron or steel from 0 degrees Celsius up to some 700, 800, 900 up to 1400 degrees Celsius, intermittent some time period after some heating, it will lose its magnetic property. Same way here, Curie point of iron is at 768 degrees Celsius, means here. Okay, so this is A2, we know A2, that is 768 degrees Celsius. Here the steel and cast iron, or we can say iron, loses its magnetic property. Means below 768 degrees Celsius our iron is in magnetic nature, and above 768 it is in non-magnetic nature. Getting or not? Means up to 0 to 768, what are all the phases present here, all are in magnetic nature, and above 768 which phases are present, all those are non-magnetic in nature. Okay, so we can say that alpha ferrite is a magnetic, austenite is non-magnetic, delta is non-magnetic. Okay, same way up to 768 all phases are magnetic, above 768 all phases are non-magnetic. Okay, next, see, the differentiation of iron depend on the carbon content is as follows. Means this is, okay, see here, from 0 to 0.008% carbon, means from here from 0 to 0.008% carbon, this is called a pure iron. This is not part of a steel also and not part of a cast iron also. This is a pure iron. Okay, from 0 to 0.008% carbon. Okay, next, see, we have steel from this 0.008 to 2%. Okay, so the steel contain again two types, that is hypoeutectoid steel and hypereutectoid steel. It is because of here we have point capital E, that is called eutectoid point. As we have studied in the second lecture, what is meant by eutectoid phase diagram? Where we have solid to solid transformation. Okay, we can see it later. First, in steel we have this point, that is capital E, eutectoid point at 0.8% carbon. So everything which is to the left of this 0.8% carbon, it is hypoeutectoid steel, and which is right to the 0.8% carbon line, this is hypereutectoid steel. Why it is eutectoid? Because here we have the eutectoid point. So what is left to the 0.8% carbon, it is hypo, and which is right to the 0.8% carbon, it is hyper. So these are the two again classification of the steel, that is hypoeutectoid steel and hypereutectoid steel. Okay, next, see here in cast iron. Cast iron also we have a point, that is small e. It is eutectic point, where we convert the liquid into two separate solids in cooling process. Okay, see here also, which is left to this 4.3% carbon, it is called hypoeutectic. Why it is eutectic? Because here we have the eutectic point in it. Okay, and what is right to it is hypereutectic cast iron. Same way, see, which is at the left it is hypo, which is at the right it is hypereutectic. Okay, so again cast iron we have the two classifications. Hypoeutectic cast iron, that is from 2 to 4.3% carbon, and for hypereutectic we have 4.3% to 6.67% carbon percentage. Okay, so this way the steel is classified into two, that is hypoeutectoid steel and hypereutectoid steel. Cast iron is classified into hypoeutectic cast iron and hypereutectic cast iron. Okay, so next, it shows the phase changes occur during the heating and cooling. As we are going to increase the temperature of material, it is a heating process. As we are going to cool the temperature, it is decreasing temperature. Okay, so this, when we heat the material and when we cool the material, is always show the phases. Okay, so we will move to the next one. See, we are going to the phases. As we know, total there are 7 phases. So this is first alpha ferrite phase, this is delta ferrite, austenite. Here we will have the, from this to this much, this all these are the cementite phase. Next we have liquid iron, next we have laterite and the perlite. Total 7 phases are there. We will go through one by one. In that also, just first 4 are the most important. Those are the alpha ferrite, delta ferrite, austenite and cementite. Okay, see first, see, we are going to divide, or we are going to describe every phase on a few points, like what is a structure, what is the maximum solubility, either it is hard or soft, which type of solid solution it has, and what is its magnetic property. Okay, see, in first way I say something. See, steel is generally softer than cast iron. Okay, so all the phases which are present inside the steel, okay, from this to this much up to 2% carbon, it is everything under a steel. So those phases which are present for a steel or in steel are the softer ones. Okay, and those phases present in cast iron is from 2 to 6.61%. Those are the harder ones. Okay, so just aware about it. Okay, same. Next, first one is alpha ferrite, where it is actually, see, this alpha. Alpha is nothing but this is phase from this 910 to up to this like 0, from 0 to 0.008% carbon. From above this we are going to like this up to this is 0.025% carbon, and again up to this one. This total is a alpha ferrite phase. Okay, so see, first in structure will be BCC, because as iron is allotropic nature, from 0 to 910 we will have a BCC structure. From this to 1400 we will have the FCC structure, and for above 140 we will have the again BCC structure. So for alpha ferrite we will have the structure as BCC, that is body centered cubic structures. Okay. Then maximum solubility, this is a point where, see, in phase you see the extreme right point of the phase, you see the extreme right point of the phase. In alpha ferrite this is the extreme right point. For austenite this will be the extreme right point. For delta this will be the extreme right point. Same way. Okay, So for alpha ferrite, this is the extreme right point. Extreme right point. So this is a maximum solubility limit. This is maximum solubility, or you can say extreme right point is nothing but a maximum solubility. Okay, so here we can write 0.025% carbon at 727 degrees Celsius. Means see, from this we get lower. This is at 0.025% carbon at temperature 727 degrees Celsius. Means alpha ferrite can dissolve maximum 0.025% carbon at 727 degrees Celsius. This is the maximum entity that can, or the maximum quantity that can alpha ferrite can dissolve. Okay, so this is the maximum solubility. Next, hard or soft. As it is a in steel, it is a soft phase. Next, type of solid solution. This is interstitial solution of iron and carbon. What do you mean by interstitial? Interstitial means the solute atoms will take place at interstitial sites of a solvent atoms. So as iron have the higher size, carbon have the low atomic size, it will form the interstitial solid solution of iron and carbon. Okay, then magnetic property. As we know, 768 is the Curie temperature of iron. Means below this everything will be in magnetic property, above this everything will be in non-magnetic property. Okay, so our alpha ferrite will be in magnetic state up to 768. Up to this, alpha ferrite will be in magnetic state. Above this, from 768 to 910, it is in non-magnetic state. Okay, so this is what about the alpha ferrite. It is having BCC structure. It is 0.025% carbon at 727. It is its maximum solubility, means extreme right point. Okay, then it is hard or soft. It is soft. Type of solid solution, that is interstitial solution of iron and carbon, and it is magnetic up to 768. From 768 to 910, it is non-magnetic. Okay, next we will see about the delta ferrite. Where is the delta ferrite? It is here, that is delta. You can see from temperature 1400 to 1539, and from this is a curve. Okay, so this is a separate delta ferrite phase. It forms only at a higher temperature. See, alpha ferrite it forms at lower temperatures, the delta ferrite forms at higher temperatures. Okay, so we are going to study again. What is the structure? As we studied above 1400, the iron will show the BCC structure. So this is BCC. What is the maximum solubility? We will see here the maximum or the extreme right point. Here is the extreme right point. This is 0.1% carbon. So maximum solubility will be 0.1% carbon. But at which temperature? This is 0.1% carbon at 1492 degrees Celsius. This will be the maximum solubility, which is 0.1% carbon at 1492 degrees Celsius. Next, either it is hard or soft. As this is in a phase of steel, it is a softer one. Okay, then type of solid solution. Again it is a steel, so it is interstitial solution of iron and carbon. Magnetic property, as you know, above 768 everything will be a non-magnetic nature. So delta ferrite also a non-magnetic in nature. Okay, you are getting or not? Simply go through the structures, maximum solubility, hard or soft, solid solution, magnetic property. Okay, simple points are there. Next, we have again two separate phases. First, austenite. Where it is? See, this is austenite phase. Start from this 727 degrees Celsius temperature and 0.8% carbon. From this up to this, all this area is bound to be austenite. Okay, this will be the austenite. See, what is the structure? The most type of structure you can say. See, from this up to 910, here we can get the BCC. From this to 1400 is will be the FCC, and from again this to this end will be again BCC. But the most of the portion falls under the FCC structure, so we will say the FCC structure, that is face centered cubic structure. What is the maximum solubility? We can see the extreme right point. This will be the extreme right point. What is the carbon percentage here? That is 2%. What is the temperature? That is 1147. So maximum solubility will be 2% carbon at 1147 degree Celsius. Means austenite can dissolve 2% of carbon at 1147 degree Celsius carbon temperature. Okay, so it is hard or soft. As it is a phase of steel, carbon below 2%, this is a softer phase. Next type of solid solution, again it is a steel, so it is again interstitial solution of iron, carbon with some manganese and nickel. Okay, magnetic property, as we know above 768 everything will be non-magnetic, and most of the portion of this austenite is in non-magnetic phase, so austenite will be non-magnetic. Okay, next fourth one, cementite. Where is the cementite? That is Fe3C. Here the whole portion, all this portion will be of cementite only. It is the hardest phase in iron carbide equilibrium diagram. Remember it. Okay, this is the hardest phase in iron carbide equilibrium diagram. Structure BCC and FCC. Why? Because cementite starts from here, from 0 to 910 we get BCC, and from here to up to this end we get the FCC structure. So it combines both BCC and FCC. Okay, then maximum solubility. For this point, what is the extreme right point? Here doesn't we have a point, here we have the extreme right line which show you the 6.61% carbon. So maximum solubility will be 6.61% carbon from where? From 0 to high temperature. So maximum solubility will be 6.61% from room temperature to high temperature. Okay, then it is hard or soft. As it comes under the cast iron, so it is a harder one. Types of solid solution. This is intermetallic compound. This is not interstitial solid solution. This is an intermetallic compound of iron and carbon, so it is a harder one. Okay, then magnetic property. Cementite will have the different Curie point. Okay, this 768 is for whole structure, and for cementite we have separate Curie point. This 210 degrees Celsius is the Curie point for cementite. Okay, from 0 means this line up to this, cementite will be in magnetic state. From 210 to above it is in non-magnetic state. Okay, just remember this small difference. This 768 degrees Celsius it is for whole phase diagram, and this 210 degrees Celsius is only for a cementite phase. Okay, 0 to 210 it is in magnetic state, and from 210 to above up to high temperature it is in non-magnetic state. Okay, so these are the four important phases. First is alpha ferrite, here we have, then delta ferrite, here we have austenite here, and here we have the cementite. These are the four important phases in iron carbide equilibrium diagram. Okay, so next, these are just to have the introductory part. Okay, first liquid iron. Liquid iron is the here, this is all liquid part, and this is only one liquid phase present in iron carbide equilibrium diagram, rather all are the solid phases. Remember this, only liquid iron which is present at the top, it is in a liquid phase, all other are the solid phases. Okay, it consists of iron and carbon in liquid state. Okay, and liquefaction temperature changes as per the carbon content. Means this is a melting temperature line, because above it we have the liquid, below it we have the solid. So this is melting temperature line, or this is liquefaction temperature line. Okay, this will change as per the carbon composition. This is not a straight line, so it is changing. It is changing as per the carbon composition. Okay, next, lead borate. Where it is? This is lead borate. Okay, see what it have? Austenite plus cementite. See, it is a eutectic mixture of. Why it is eutectic mixture here? Eutectic point is there, so this is eutectic mixture of austenite plus Fe3C. Okay, same way we have here, we have the perlite, that is again a eutectoid mixture of alpha ferrite plus Fe3C. Okay, so these are the 7 phases present in iron carbide equilibrium diagram. Those are alpha ferrite, delta ferrite, austenite, liquid iron, cementite, lead borate and